Yeah. Another way to solve this recurrence relation is to use linear recurrence relation, which we know how to solve it. Okay. So here what we do is introduce another variable k such that n in the k has this following relation. The reason, of course, is because here each time we divide n by b. So we keep on dividing it. Eventually, in order to get 1, we divide it by k times. So where k is a value depending on n. All right. So then we can get a linear recurrence relation based on the k instead of this above this recurrence relation. So we see that n divided by b is become k minus 1. Now n is replaced by b to power k. That's what we get. So we get a non-homogeneous linear recurrence relation. So that's the non-homogeneous part. So this one is fk. All right, non-homogeneous are the form of here c times s to power k. Of course, here c is a constant. Here c is a constant. Some positive constant, right? Now, since we have non-homogeneous recurrence relation, we know how to solve it. That's a linear one. Okay. So its solution consists of two parts. One is homogeneous part. That's whose solution depends on its characteristic equation, which is r minus a equals 0. So where roots, of course, is a single root r equal a. So from here, we know the homogeneous part. Solution of homogeneous part is of the form alpha times, say, a to power k. So this constant need to be determined. Now, for us, in terms of big O notation, we don't care about this alpha. In terms of big O notation, so we can just say this one is big O of n to power k. Okay. Now for the non-homogeneous part, a particular solution of non-homogeneous one is of the form of non-homogeneous part if S not equal A. Otherwise, will be K times this form. So there are two different situations. All right. So this one will equal to exactly this form. So in some big O notation, we don't need to care about this C. So it's just big O all right. So if this S equal this one, so A not equal B to the solution is of this form. Otherwise, A equal B to power D. So in this case, solution will be this part times K. So in terms of big O notation, we don't need to care about this particular constant. It's a constant. So it's K B D to power K. Right. So we know the solution for this linear recurrence relation. Now what we need to do is replace K by function n to get back solution of this one in terms of n instead of solution of this one in terms of k. So of course here, because this relation, we have k equals log b. All right, now we replace it k by this one to get a solution in terms of n. Okay, so let's see what happens. Okay, this part is easier maybe. It's a b dk equals dk d, which is nd. Exactly nd. All right. So this one, what we have, to replace this part by n to power d. So this one actually give us order n to power d, here order n to power d times the n, right? So for these two situations, we have solution here. All right. Okay, now for this part, a to power k. For the homogeneous solution, a to power k. Does it equal this one? Now this one does not look like n to power something. This one does not look n power to power something. It looks like exponential function. Actually not, because here exponent part is logarithm. We can transform the whole thing into a polynomial. Actually, it's equivalent to a polynomial. Okay. So here is one way to make it, to transform it into a polynomial. So n can be rewritten as a to power log a n. So just replace n with this one. We get a log a n. All right. So then, of course, this one equals a log a n times log b a. Now this one exactly same as this one. So that gives us n to the power log b a. All right. This one, the solution of homogeneous is order n log b a. All right. Now we solve everything. We already expressed solution to GK in terms of n. The solution of GK is summation of these two parts. Now, in terms of bigger notation, value of this one is depends on which one is bigger. This one is bigger and of this one is bigger. By big, I mean which one grows faster. So in this particular case, we just need to compare this one with one of these two to see which one dominates. All right. So that's very simple. So once we see that to the attribute that we have the following. So the final solution will be, say you just color Tn equal so either order of n to power d. This one dominates or this one dominates. When we compare these two, of course, this one is larger than that one. This one is larger than this one. Remember here, d equals log ba in this case. So d2 equals this exponent part is exactly d. So, but here there's a factor of logarithm. Of course, this one dominates. Here is n to power d log en. Otherwise, this one dominates. So function of Tn is either this one or this one or this one. Depends on which one is bigger, a or b to power d. So here is a equals. So here is d is larger than log ba. Here d is smaller than log ba. So of course this one same as that equal. Okay. So d equals log ba. Right? So therefore we solve this reconciliation. I transform it into a non-homogeneous linear reconciliation. Then solve this one, and we obtain solution for TL. It's very important, very useful for this solution of this reconciliation. It's very, very important when we study algorithms, in particular divide and conquer algorithms, when we need to analyze running time of algorithms. And I do hope that you can remember this formula. That was not all cases of divide and conquer, but for most important ones, their running time will be determined by this difference relation. And therefore, we do have formula for the solution of such difference relation. And again, I emphasize do hope that you can remember this one. Okay. Very likely, this one will be in exams. All right. Okay.